So if you remember last time, we continued to the two-stage amplifier design and we did calculations for its omega naught, dominant frequency, parasitic pole, and then we also see, okay, how is the effect of compensation capacitor, and also then we added the compensation resistor and why we need the compensation resistor RC, which is at this point, and we did the equation for the, or the value for the omega z pole, and then how that RC was getting rid of that omega z pole. So we'll start from the same point. And today what we are going to do, we are going to put some specifications, meaning some numerical numbers, like a gain is this thing, gain bandwidth is this one, we need a phase margin of this value, we need a slew rate of this value, and we will try to analyze, okay, how we can achieve using this two-stage basic amplifier those specifications. And that will be somehow also your complex engineering problem, but with different specifications, and you need to simulate that. So let's just put those stuff which we covered in the last lecture, so we get an idea that, okay, we saw something that this is omega for us in radians per second. And if we just talk about our bandwidth, some sort of, so we talk about this one and we talk for the second pole. So we said this one was our omega naught. This here, sorry, this one was omega p1 at some frequency where it reaches a 0 dB. So that was omega naught for us, and this point was omega p2 for us. And then we also said, okay, we are also going to have something omega z here, and this was k for us. So if 20 log k. If we recall the values just for a, because that will be used, so we just write it somewhere, all of them together. So omega p1 was, after adding the compensation capacitor, it shifted more toward the left hand side, and the value was GM6 RO2 in parallel with RO4 times RO6 in parallel with RO7, and then they were multiplied by the compensation capacitor CC. So that was the basically this omega P1. Then if you recall omega P2, after adding the compensation capacitor, we assume that this is going to be act as a short, so we can just see approximation behavior was somehow dependent on GM6 divided by CL plus CGS6. So that was omega P2 for us, second pole, the non-dominant pole. And then correspondingly, we also placed omega naught. We placed one magnitude in the h of omega equation to find the omega naught. So omega naught came out to be GM1 or 2 by CC, compensation capacitor. So these are all, those were on the x-axis regarding the poles. And also we figure it out, omega z was a negative frequency. So the omega z was somehow equivalent to minus GM6 divided by, so the omega 6 was also dependent on CC for us. And then we just figure it out. Okay, if we just want to find out this value, we can just write directly CC. So omega z was equal to minus GM6 over CC. And I'm assuming now there is no RC. So RC is not there. When RC is going to be there, then this is going to be compensated. So let's, as a, for the design purposes, initially assume that there is no RC. So there is no RC. Okay. So these were basically those relations which we figured it out in last lecture, and also we started the two-stage amplifier one lecture back. So we'll start from the same point. So before going to the slew rate, let's put some specifications first. and then we are going to talk about the slew rate. Let's make it at 8A. So here are some of the specifications of the design which we want to do. Okay, so we have some specifications which we need to work on. What are those specifications? They are those based on which we are going to do the design, provided to us by the some our vendor, some or specification requirement from our application that okay, what is my, for example, gain bandwidth, right? What is my gain of an amplifier? What is, for example, my slew rate? After the slew rate, what is the value of load capacitance? Because load capacitance is something is going to be provided to me as a designer. So that's also something which is I will place at a load capacitance value. कितना load मैं अपने system में या जो भी आपने application की ली है, how much is the load capacitance you want to give directly to the oscilloscope. So if you are giving directly to the oscilloscope, then you are having the load capacitance seen by the cable of an oscilloscope. If you want to feed it to some other PGA, some other ADC, whatever the thing, you need to have guess or you need to have an idea about the load capacitance. That load capacitance should be provided to me as a designer because my design is highly dependent on that value. So after the gain, the slew rate, the load capacitance, the another thing is PM, phase margin, which we also have previously seen what is the phase margin, but I need to we provided my phase margin as a specifications. I want my system to be stable, but how much? As we mentioned, how much? Is it a 45-degree stable? Is it 60 degrees? Is it a 30-degree? Whatever the stability is going to be required, I need to design based on that requirement. So I need a gain bandwidth, I need a gain, I need a slew rate, I need a load capacitance, I need a phase margin. What else anybody thinks? What else can needed for this one? So today is like more like a design. I would like if you can also do contribution. So it will be great if you take participation, so all of us can follow easily. So what else do you think in a specification of an amplifier should be provided to you so that you can just do calculation? In reality, there should be a noise. हम लोगों ने noise discuss नहीं किया in this course. That's an advanced topic, for example. So we might not do or analyze at this moment, but that should also be provided in systems. Anything else? Try to think what can else be the values that you need basically.
Do we also need the gain margin like we have the phase margin?
Gain margin, we don't use explicitly gain margin. We normally want gain, and gain should be strict. Like if I want my system to have a 40 dB gain, this means I need a 40 dB gain. ठीक है, so वो gain में आ जाएगा, gain margin नहीं होगा. So definitely we need a gain, but that is going to be in the gain categorization, not in the margin sort of stuff. ठीक है, phase margin एक इस value तक होना चाहिए, इससे कम नहीं होना चाहिए. ठीक है, if I am putting my phase margin at 60 degrees, this means even if I achieve 70-degree phase margin, well and good, but I don't want to go below 60 degrees. ठीक है, तो वो हाँ मकसद हो जाता है. Gain में ये भी आप कह सकते हो कि
what if how about the power specifications of
yes,
the amplifier?
power is going to come here. Definitely power is one of the main budget. Based on power we need to have कि हम लोगों ने power कितनी है मेरे पास system. Power is going to be definitely one thing. Based on that, which I need to also do. Anything else? थोड़ा सा I want you all of you to think कि हम लोगों ने क्योंकि two stage amplifier अभी देख रहे हैं, two stage is basically a differential amplifier, and there is something else you think can be required. It somehow we covered in this course or didn't cover, but you think it's important.
Sir, CMRR.
CMRR can also be right. So let's say the brother of CMRR, PSRR should also be important. Again, we didn't cover with respect to two-stage amplifier, but we definitely need to take into account the CMRR, PSRR in a configuration. Anything else which is very much important for the design?
Sir, input common mode range or the settling time.
Right. So input common mode range. So that is something. There are two values: input common range positive, input common mode range negative. Let's basically start from this point. What is this input common mode range positive, and what is this input common range negative, or input common basically? I wouldn't say there is something wrong I wrote. It should be ICM positive, ICM negative, and the range is going to be from ICM positive to ICM negative. So this is my range. So if I want to write ICMR, this should be something like this. So just try to see what is going to be here. हम लोगों ने एक रेंज लिखी है ICMR, इसका मतलब क्या होगा? Anybody want to say okay, what is the meaning of this ICMR range? हम लोगों ने लिख तो लिया, but what is the meaning? Try to little bit link with an amplifier जो हम लोगों ने डिजाइन किया था, उसमें क्या चीज थी? इनपुट साइड थी, क्योंकि ICM मीनिंग इनपुट कॉमन मोड रेंज, सो इट शुड बी इनपुट रेंज. ठीक है, तो इनपुट रेंज की अगर बात करें तो ये हमारे पास ट्रांजिस्टर था जो हम लोगों ने अभी डिफरेंशियल डिजाइन कर रहे थे टू स्टेज का. उसकी पहली स्टेज पे इनपुट थी, VN नेगेटिव हम लोगों ने कहा था आ रहा है, VN पॉजिटिव हम लोगों ने कहा था आ रहा है. ठीक है, सो that range of input which will ensure कि हमारे पास उसके आगे एक लोड लगा हुआ था. ठीक है, VDD था, together, and then there was this thing. ठीक है, that input range और DC value of input जो मैं यहाँ अप्लाई करूंगा to ensure my this transistors M5, M1, M2, M3 and M4 all of them remain in saturation. क्योंकि जो AC सिग्नल आप देते हैं that is just for the amplification purpose, जिसको आपने amplify करना है, but in order for that to amplify your transistor should remain in saturation. वो saturation कौन achieve करता है? A DC value जो आप इस ट्रांजिस्टर को अप्लाई करते हैं, which should be like VGS should be greater than V threshold or VDS should be greater than VGS minus VT. That DC value should be provided by a designer. अगर वो डिजाइनर ने प्रोवाइड करनी है, then that should also be taken into consideration जब हम ये सारी कैलकुलेशन गेन बैंडविड्थ की, स्लीव रेट की, फेज मार्जिन की, नॉइज की करेंगे. It should also be taken into account. So that's why it's very much important. I should know before starting a design what's my common mode range, meaning कि मैं क्या common mode signal दे सकता हूँ या दूं तो ये ट्रांजिस्टर, ये ऑपरेशनल एम्पलीफायर सैचुरेशन में रहे. फॉर एग्जांपल अगर मैं कहूँ मेरी रेंज है 0.5 से 1 वोल्ट, my negative ICMR negative या small value is 0.5 and maximum value is 1 volt. ठीक है, so my transistor, my this operational amplifier should remain in saturation. अगर मैं इनपुट पे 0.5 दूं, 0.6 दूं, 0.7 दूं या 1 volt तक दूं, this operational amplifier should operate, meaning all of the transistors should operate in saturation. के ऊपर जो specification है, they should meet for these values for 0.5 to 1. और वो common mode है तो same value input side पे होगी और same value output side पे होगी. So this ICM is very much important in that sense. Any question related to the ICM thing? Then we'll put some numbers to start the design.
Sir, Just one thing regarding ICMR. So you basically said that it is the value of DC gain for which the system is in saturation.
All the transistors should remain in saturation. Yes.
Okay. Thank you.
ठीक है. So let's put some numbers. तो हम लोग design start करने के लिए we will use those numbers and we'll develop the topology. So for example, gain bandwidth is 30 megahertz. ठीक है. Gain bandwidth का मतलब क्या होगा आपके पास? It's basically omega naught. ठीक है. Maximum bandwidth of your system at a unity gain. So 30 megahertz. Given gain, for example, is provided to you is 1000. आपने इसके बेस पे डिजाइन करना है. अभी हम आते हैं कि what is meant by design. We need the specification. तो हमने डिजाइन अब क्या करना होगा? Slew rate. We will just open up the topic of slew rate in just couple of minutes. So the slew rate is 20 volts per microsecond. Load capacitance in this design we are making it as a 2 picofarad. Okay. Phase margin, for example, just so now either we take 40 more than 45 or a 60 degree. 60 degree is more better, so we go for a 60 degree. Noise, हम लोग इसकी बेस पे अभी नहीं डिजाइन कर रहे, but let's put if you want to have a feeling of the noise, you can have, let's say, means for your band of interest, or in terms of nanovolt, we can have like a 10 nanovolt per hertz. Noise is all the time in the form of power or power spectral density. So it's going to be in this form. It's volt square per hertz. Since we didn't cover in this course, we are not going to talk much about that one, how we are going to achieve this thing. But at this moment, there are the specifications जो भी आप design करते हैं, it's going to be provided to you. Power, for example, हम लोग इस design में ले सकते हैं 300 microwatt. CMRR, again, we will not do the CMRR design based on CMRR, but we can see later on tricks how we can enhance the CMRR. So CMRR should be a relatively a good value, and that totally depends upon your input signal value. का आपका input signal 1 milliwatt का है, 1 microwatt का है, then based on that you can decide कितनी आपको noise reject करनी है, so that still you can have a good signal. So, but in any case, the more bigger value, the better it is. But definitely the design becomes complex. So हम लोग place in कर लेते हैं, ठीक है, something bigger than 80. ठीक है? CMRR should be more than 80 dB. PSRR, power supply rejection ratio, should also be bigger than 80 dB. ठीक है? ICM की जो values हैं, so we should have ICM plus should be 1.6 volts. And ICM negative 0.8 volts, meaning I want my operation amplifier to operate from 0.8 to 1.6 volts. ठीक हो गया. Two more important things हम लोगों ने नहीं mention की are basically, let me just write here, VDD, supply voltage कितनी है, ठीक है? So we are taking a supply voltage of 1.8 volts. And then also another important thing is आपने जो amplifier design कर रहे हैं, you are using a real transistor, so there should be some channel length, minimum channel length or technology associated with that. So what we are talking about a transistor with a minimum channel length of 0.18 micron or 180 nanometer, meaning जो minimum channel length होगी या minimum length होगी transistor की, आप 180 nanometer से नीचे नहीं जा सकते. ठीक है? Why? Whenever you design an amplifier, you want to do a real design. Real design means it's going to get fabricated in a foundry. तो जब आप foundry से fabricate करवाएंगे, so you need to consult the foundry कि उन्होंने कौन सा वो design use कर रहे हैं, कौन सी technology वो support कर रहे हैं, and then so that they can do that fabrication process for you. And also while you are designing, you need some values. For example, mu naught COX, mu P COX. So you need mu n COX. You need mu P COX. So they will be also provided to you by the foundry, right? So these